Well, let's look at composition of mixtures. AP sections are not all the same. Some are so small, they're almost not even worth mentioning. And some are gigantic, huge, and will take at least 2 classes to talk about. This is one of the small ones. However, it's a key and essential one that they talk about is representations of different things. So often we'll show elements and molecules, of course, as small spheres. When they're conjoined, that means they'd be molecules, okay? Mixtures may be atoms of different color, different sizes. Of course, we have atoms mixed with molecules that are different of each. And then you have things that are a compound where you can see that they have different colors, different sizes. Now, as far as I know, the AP test is all black and white. So they often will sometimes label stuff. So I try to give you as many iterations of what this looks like so you're aware of what to write and how to use it. The number one key is use what they give you. If they give you things that look like this, use them. If they give you things that look like this, use them. Always use their guide is what they have. I don't think I've come across any questions that just say, draw this without giving you any examples of what that would look like. All right. But again, pure substances, you have something like this to where you can see compounds lined up, elements, mixtures, different sizes, different colors, homogeneous, showing that the factors that there's not the same amounts of each, or they're not in the same structure. Heterogeneous, showing you that there's uneven balance between these. States of matter, gases are farther apart, liquids are touching, solids are like you can say in a shape, blocks, structures, is also key. Sometimes they show reactants and products, so showing that different elements are now formed to make new molecules. Again, physical changes, solids to liquids, showing different things of orientation, meaning how they are oriented in space. So sometimes there's going to be later parts to where we have ions, and you'd have the positive ion attracted to the negative ion, so they would be lined up, as opposed to them being two positive ions touching or so close to each other. Solubility is also popular, so showing how something's dissolved. So for example, you have down here a block or crystal of sodium chloride. You can see the structure is correct with positives attracting negatives. You can see that the negative ions are generally going to be attracted to the positive ones. That kind of shows a misnomer here. But you can see the ions that are positive are attracted by the negative parts of each water molecule. So this is the orientation side I was talking about, while a negative ion is aligning all the positive ions or positive parts of water. So again, showing this would be a great example. Not to this detail, it's pretty rudimentary, okay? You don't need to be an artist to do well on this. But also thinking in phases, what happens to water without a lid? Well, you'd have some of it evaporate, but you can see this is gas, this is liquid. And again, showing liquids, showing that there still is a gas in form. This is why you have condensation on your water bottle when you leave it in your car or even overnight. You have this becoming gas vapor. So these are all just representations of how images should look, and you should really get used to practicing them with our practice that we have online in labs and so on. It seems simple, but oh my goodness, it's an easy way to lose some points on an FRQ. Now, one part that does come up in this section, and it really doesn't in our Pearson book, I had to find some other examples to use, involves our ability to, go back, there we go, because these are representations and composition of mixtures. So this is a visual sense of it. And then we have a calculation side. So often similar compounds end up in a mixture we thought was pure. So you might have a little bit of magnesium chloride in a large sample of sodium chloride. Because they react very similarly, it's hard to separate them out. So here's one example. You have 15 grams of barium oxide actually has some contaminant, sodium oxide, and you know that there's 0.6 grams of sodium. How much sodium oxide is in the sample? The formula for sodium oxide, Na2O. So this goes back to when we talked about conversions of going from like our lead chloride that we had and seeing how many chloride ions there were. So This is taking those chloride ions and putting them back into the compound itself. So what we do is we have our grams of sodium, moles of sodium. I see that there's 2 sodiums for every 1 oxygen. Don't always assume it's going to be a 1-to-1 ratio. Depends upon the chemical formula. Then I have the molar mass. So based off having 0.6 grams of sodium, I have 0.81 grams of sodium 2 oxide. I'm sure there's another way you could do this with mass percents. Conversions is a good way of going, but again, showing your work, labeling your units, labeling your compounds, totally necessary to get points on the AP test. So if this is my contaminant, I actually have so much barium oxide. So then I should expect to have 15 over the actual. That means my compound is 94.7% barium oxide. So that's one part of it. Another part of the AP test is to understand and say, okay, it's not pure. How would that affect my results? So that's usually where we talk about is if you had a chemical reaction of barium oxide when Na2O wouldn't react, what would that say about the expected mass? Well, that plays a role. It depends on what it reacted with. Because if this wouldn't react, it would be still found there, your 0.81 grams, but based upon your component, it might make the actual reactant less, because if I'm expecting 100% to react and only 94.7 reacts, my mass should be less than I expected. These are the things that are the biggest challenge, I'd say, to the AP test, aside from the breadth and depth of some of the content. So some other small math that comes up in this section. You'll see mole fraction. So that is just an example of 1 mole of your unknown or your contaminant over the moles of the total. So you'll see these terms come across in the AP test, and they're really not too complicated. They're just kind of the terminology that comes up. A mole percent, you take that mole fraction, make it into a percent, kind of like we talked about with the percent contamination of our previous problem. And then you have a mass percent. So if I've got 10 grams of this, how much is the contamination, and so on. So you can have a mole percent, not as useful in the real world. Mass percent is more useful, much like what we had back here, where we had a mass percent as opposed to a mole percent. Because a mole percent, I'm not sure exactly what that would deliver for you. But again, if they ask about it, you need to be able to do it. But again, percents are just our unknown divided by our total, whether it's fraction, a percent times 100. It's really math that you should be pretty familiar with based upon being in the course and taking math aplenty. Let me know what questions you got. I'm here to help. Take care.